Okay, so as a recap, we use integration by parts to turn a hard integral into an easy integral. Integration by parts is just a formula that we got from doing the product rule for derivatives, but backwards, right? That was our whole integral of v du equals u times v minus integral of u dv. And you can see my previous video to follow the algebra for where that formula comes from. When do I use it? And how do I know what part of the integral goes where? That's the point of this video. So we're going to use integration by parts anytime we have the integral of the product of two different functions. Integrals of the sum of two different functions are really nice. You just do the integral of the one plus the integral of the other. Super simple. For products, we got to work a lot harder. It's just the way it's got to work. So sometimes I can get away with a u substitution. Maybe if I have the product of two different polynomials, I might be able to use a u substitution there. And if I can use a u substitution, I will. I like to keep things as simple as possible. Integration by parts is a harder technique that I only use when my u substitution isn't enough to cut it. So here's an example problem. I want to calculate the integral of x times the sine of x dx. And this one I can't use my u substitution. Well, first off, I say, if it was a u substitution, I'd try to find that innermost set of parentheses. And I got an x, and I got a sine of x. Derivative of sine of x doesn't give me an x. Derivative of x doesn't give me a sine of x. So this is not going to be a u sub. Instead, I'm going to use the formula from my previous video. Integral of u dv is u times v minus the integral of v du. We're going to turn one integral into another, and this u times v is going to pop out. That means when I'm looking at this formula, x times the sine of x, one of those pieces will be the u in my integration by parts formula. And when I change this formula, right, I'm going to pop out that u times v, my u will be replaced by the derivative of u. The rest of that integral, right, the other part that it's not the u, that's the dv. The dv gets replaced by its antiderivative. So when we're making this change, we want to use this knowledge to make sure that my new integral is actually easier than what I've got and not harder than what I've got. That can happen sometimes. So I like to set up my Scratch work looking something like this. Here is the integral I want to solve. I'm trying to solve the integral of x times sine of x dx. One of these functions is going to be my u, and one of them is going to be my dv. So I fill out a grid. First row tells me all the stuff I got to know about the variable u. Second row tells me all the stuff I got to know about my variable v. And I'm going to fill in my opposite corners. I picked u equals x. And the reason I picked u equals x is because the u is going to be replaced by its own derivative. The derivative of x dx is 1. And what could be a nicer derivative to work with than 1? That means, because I made that choice, the dv has to be my sine function. strictly speaking, it's going to be sine of x dx. The differential comes along for the ride. That's my dv, so I put it in the bottom right corner there. Now, the dv is going to be replaced by the antiderivative of the sine function. So I'll get some flavor of cosine, and that's at least not worse. So I've got one part of my integral that's definitely getting easier. The x is becoming just a 1. And I've got the other part of my integral that at least is not harder. So one part is easier, one part did not get harder. That sounds like an easier integral to me. Fingers crossed that'll work out. But that's the reasoning I'm using for this formula. Now, I've found my opposite corners. I know what u is, I know what dv is, and I need to use my knowledge of derivatives and antiderivatives to fill in the rest of my chart. Got that on my next slide here. U is still equal to x, and this means that du is equal to dx. Well, hey, u and x are the same thing, so their differentials are exactly the same as well. For the v's, if I have a function sine of x and I'm trying to find its antiderivative, I'm going to have minus the cosine of x. It's always a little bit tricky with those trig functions to know when you've got a plus and when you've got a minus. I can double check. The derivative of a cosine is minus the sine. So if I'm taking the derivative of minus a cosine, I will get minus a sine, which is a positive sign. So double check looks good. I've also copied down the integration by parts formula here with the u's and the v's. So this is the kind of stuff I would be doing on my Scratch work. And I can say that this integral here is equal to this formula on the right. So let me just take in all of my ingredients and follow this recipe, see what I get. First part of the recipe, u times v. So I have x and I have minus the cosine of x. I've gone ahead and written them down here as minus x times cosine of x. The order of the multiplication doesn't actually matter, but it's nice to put that minus sign out in the front just to make it easier to read the equation. Okay, cool. Next, I got to subtract off the integral of v du. So let's populate those variables. V becomes a minus cosine of x, du becomes a dx. So now this integral up top is actually equal to the integral of minus the cosine of x dx. Do be careful here that I'm integrating minus the cosine, and I need to subtract that integral. So integration by parts does require a lot of bookkeeping. That's part of the reason I like to write out the variables and their differentials in this way. And I'm going to keep this negative sign just the way it's written here. You could also pull the minus out and do plus the integral of positive cosine instead, but that's not how I wrote these notes. Now, the only thing that I have left to do for this problem is to simplify. This is the integral that I've been asked to calculate. What is the integral of x times the sine of x dx? My integration by parts formula says that this integral is equal to minus x times the cosine of x minus the integral of minus cosine of x dx. I already cleaned up that outside bit pretty well. And I'm going to subtract off the indefinite integral here, or I'm going to subtract off the antiderivative. So what is the antiderivative of minus the cosine of x? Why, that is minus the sine function. Again, I can double check. Derivative of positive the sine is positive the cosine. So derivative of negative the sine is negative the cosine. Cool. And because I'm doing an indefinite integral, as always, it's got to come with its own constant of integration. That's our good old plus capital C. So in my first step of cleanup, I have calculated my antiderivative, and I get that this integral that I'm interested in is equal to minus x times the cosine of x minus quantity negative sine of x plus an arbitrary constant. I'm going to distribute that negative through the whole thing there. Minus negative sine of x becomes plus the sine of x. And I'm being a little fast and loose with that constant of integration. I put that there because antiderivatives are not unique. Functions have lots of different antiderivatives. Any particular function will have lots of different antiderivatives that are different by some constant. So maybe today my antiderivative is sine of x plus 1. Maybe tomorrow my antiderivative will be sine of x minus 37. Those are both valid antiderivatives. Since the c is just a placeholder here, I could have written minus the constant c, but since I already don't know what number that is, it doesn't make a whole lot of difference to say minus some number I don't know, which could be positive or negative, or plus some constant I don't know, which could be positive or negative. So it's common to see stuff like this where it looks like I should have distributed through that minus sign, but I didn't, just to make the formula a little cleaner at the very end. Anyway, that was a tangent, except this is a sine. So the answer for this integral is that the integral is equal to minus x times the cosine of x plus the sine of x plus c. And I am done.